We're going to deal with this fabricated scenario where we are imagining we're going to go out and measure a bunch of IQs for a sample of a population. We want to do inference on what that population's characteristics are. So we're going to use a generative model such that we're going to say the population has this normal distribution with sort of a variability parameter, sigma, that we're going to assume that we know. So we're going to set it to being 15. We are certain that the population has a variability of 15. This is actually rare in the real world, but just as a toy example, it allows us to reduce the complexity of our model a little bit. A normal distribution has two parameters. One is sigma, which we're saying is fixed at 15. The other one is where it's located on this x-axis. So what are the values down here? Another common name for that is mu. Actually, you could put it as the Greek symbol mu. And so the question is, before we see any data whatsoever, what do we believe about this thing mu? So I'll actually shove down a little bit. And if we actually ask ourselves, if we sort of have an axis here where we say, so have an axis where we've got credibility on the y-axis. If you're somewhat familiar with IQ tests, you might assume that the value of 100 as the mean for the population that we're going to draw samples from is a fairly credible value without having seen any data yet. If we have, say, 140, that's probably not going to be so credible. Ditto, if we had, say, 60, that's probably not going to be so credible. You can fill in, so 80, it's going to be, I don't know, somewhere like there. Ditto, 120, somewhere like there. So you could sort of take the shape that you're kind of seeing there and make, I don't know, a triangle. That would be a little problematic because it implies that beyond some points you have sort of absolutely zero credibility in values out here. That actually might be the case. We've never seen anybody with, say, an IQ of 6,000, so it probably wouldn't make sense to actually have a distribution that goes from negative infinity to positive infinity. But it actually makes the math work out a little bit better if you use sort of a more continuous distribution that does go from negative infinity to positive infinity. So a popular, just like a popular distribution for generating data is a normal distribution, a popular distribution for expressing your beliefs is also a normal distribution. So here, well, it's critical to note that you can and we will have, hopefully by the end of this lecture, an example of scenarios where you have non-normal distributions for beliefs, and ditto, you can have non-normal distributions for the model for how the data were generated. We'll get into that, I think, next week when we start dealing with like binomial data and things like that. But for the purposes of expressing, again, we are certain that the data were generated from a normal distribution. We're certain that the data were generated such that sigma was 15, but we're uncertain about what mu should be for this population. Again, actually, we're talking about this as if we haven't even seen any data yet, so this is our beliefs about the population prior to seeing any data. So we need to express a distribution of sort of how much we believe potential values of this location parameter for the data generating model. So we can have a distribution that theoretically would be peaked at 100. A nice distribution is the Gaussian distribution. So if I sort of plot that a little bit better, that still doesn't look great. So let's imagine that I actually drew a proper Gaussian distribution. The Gaussian distribution, because we have a peak credibility at 100, the mean of this, let's call it M, is equal to 100. And the other parameter of the Gaussian, the variability, will serve to specify how confident we are that values close to where the peak is being set, how confident we are that those are credible, and sort of how incredible we want, or how much we want our credibility to fall off. So if we used let me actually sort of draw a new thing down here because this is getting messy. So credibility, we'll have 100. So if I really disbelieved that it was going to be anything other than one, if I sort of was really confident it's going to be somewhere around 100, maybe within plus or minus 5 or so, I'd maybe have a distribution, again, peaked at 100, but with a very small value for the variability parameter. Let's call that V. So that looks like a distribution with a M of 100, but it has a V of, say, I don't know, 5. Alternatively, if I didn't want to be that confident, if I wanted to express more sort of uncertainty, or inversely, more credibility in sort of more extreme values, I might choose a different distribution, again, peaked at 100, but really broad and sort of tapering off on either side fairly slowly. So this one's V might be something like, I don't know, that looks like about 30. So again, critical to remember here is that this normal distribution is just a way of shorthand express, or a shortcut to expressing a distribution of beliefs. The mean parameter sets where we think the peak sort of our beliefs are, what we think is the most credible hypothesis ahead of time. And the variability parameter specifies sort of how confident we are in that belief. So critically, that's different from this distribution. This is our data generating distribution. Here we're again assuming that the variability of how the population sort of varies from one person to another is set. We're certain that it's 15, but we're uncertain about this mu, and we'll set a prior on that value. Now, a term for the distinction between these two different sort of, this peak, very sort of strongly peaked prior, and this prior that's more spread out, you might call this one a strongly informed prior, and this one a weakly informed prior. Those are terms that you'll see out there if you start Googling the Bayesian data analysis websites. So having expressed, let's say we choose this nice, it's generally recommended you choose broad priors. Usually you can set some sort of reasonable limits on like how, or reasonable values for how uncertain you want to be. I guess the extreme is if you expressed a uniform prior across the entire range of possible values. That tends to have some computational issues. It also just has some conceptual issues, whereby that sort of implies that you equally believe, say, a value of 2,000 as 100. So it really doesn't make a lot of sense. I had a question there.
How do you set your prior? Based on the previous literature review?
Yes, so you'll often set the prior, if you're sort of a relative expert in a domain, you'll have a lot of good sort of intuition about where the prior should be. So for example, I have a lot of experience with human reaction time experiments. So I know that in sort of a typical reaction time experiment, young people will have mean reaction times around 400 milliseconds. I would believe maybe 350 and 450. I'd start getting very skeptical about like 250 and 550. So I have a feel for that domain. If you don't have a feel for a domain, you could always do like a literature search to establish what sort of previous findings are. But I'll talk about another method for establishing priors in a relatively objective way when you don't have sort of a strong feel for the domain yet, but we'll get to that in a little bit. Question?
I don't know if I should ask this
Yeah.
now or later on, but like when you look for the prior, what exactly like in the papers that would represent? Does it represent like the
Well, what are the values that they've observed in the past
like the
of real data?
scientific
Yeah. You'd sort of establish what populations have been studied in the past, where their means of those populations have been found. Yeah, and the standard deviation this sort of alludes to the technique we're going to use. The standard deviation of the populations you've observed in the past could be used to set what sort of amounts of credibility or the variability in your own credibility distribution. But I'll show you an example of that. I think we'll get to it. Yeah, I'll do it today as an example. All right, so this is the scenario in theory before collecting the data. So what happens once you collect the data? So let's imagine we get sort of a observation here, an observation there. Well, you get a whole bunch of observations. It kind of looks like, say if this were the 100 point, it kind of looks like the distribution needs to shift a bit to kind of fit the data better. But the specific sort of process by which you ask sort of how much the data, this distribution needs to fit or needs to shift is sort of done automatically by the software Stan that I had you guys install. So what Stan's going to do is it's going to take this data generation model. It's going to take your prior distribution, integrate that with the new data, the information represented by the data itself, and it's going to spit out a posterior distribution. So it's a distribution that still has the same credibility thing on the y-axis, and on the x-axis is various values for what you should believe in for the value of mu. But it's going to be a new distribution that, in theory, should be a little bit tighter than the prior distribution that you put into it. And it should be maybe a little bit shifted to the degree that the data warrant the distribution to be shifted. So let me switch over now to our R code. So we had some code that we wrote yesterday just to visualize different sort of priors. So that's this little bit up top. Let's actually pop over to our model over here. This is the Stan file. I'm going to pop it out to its own window so that it can fill. So the way the Stan files work, there's 3 sections: data, parameters, model. All the lines have to end with the little semicolon. Whenever you're sort of initializing a variable, sort of telling Stan about a new sort of variable object, you need to tell it sort of what kind of data is going to be into that. So here in the data section, we're telling it what to expect as data coming in. So we're saying expect a named thing, something named ny, and it's just going to be an integer. That's a number that doesn't take decimals or negative values. And the thing y is going to be a vector, so a sort of list of numbers, that is ny long. So whatever we put here as ny, we're telling it the vector y has this many elements in it. So having told it what to expect in terms of data coming in, we can skip down to the model section where the very last line is expressing how data relate to something. This something over here is our generative model. Remember, we said that we wanted to model the data as being sampled from a normal distribution with a known variability, standard deviation of 15, but we're going to be uncertain about what the value of the mean of that distribution is. So given that we're uncertain about this value, it gets put in the parameters section. We tell it that it's named mu. and it's real, which means that it can take any value from negative infinity to positive infinity, including decimals. So having asserted that there's this thing we're uncertain about, we then also give it a expression for what our prior on that variable is. It happens to be a normal distribution where it's centered on 100, so we think that 100 is the most credible hypothesis for how this data were generated, but it tapers off on either side to a degree. We decided that 20 was sort of a reasonably weakly informed prior. So having this file named .stan written up, it's just a text file, but having written that file, we can go back to our console and we can generate some fake data. So that's what we did up at the top here. I'll actually start from here and load everything in. So this first section generates some fake data. It's as if we went out and we actually observed some data in the real world. We're generating data from sort of a known value of mu and matching the value of sigma that we are going to assume for the data. But we're immediately going to forget that we actually set this value of mu being 100 because we're going to now pretend that this y has just been handed to us by some researchers, and we want to do some do inference on it. So we have this thing called y. It's all these values, and we want to use our model to ask about what the likely mean of the distribution, normal distribution, is for the population that generated these data. So we have to package that up for Stan. So Stan wants things to be in a list. And again, because we had two elements, ny and y says how long y is, we have to put in that list two elements, one thing called ny, which is just computes the length of y, and the other thing is just y. So having created that, it just puts it in a format that Stan can read it in. And this next line takes that text file that we wrote that has the Stan model and turns it into like an app that it's going to store in a temporary directory that it can then use. So it compiles it into a special super fast app that will be able to do all the Bayesian sampling behind the scenes that you guys don't really need to know about. So if you had written anything incorrect in your Stan file, so left off a semicolon or anything, you'll get some error messages here that try to tell you about, the error message will try to guess what you, well, it will tell you what seems wrong, and from that you can try to guess what needs to be corrected. If you haven't made any mistakes, at least as far as the making code that is will compile, it will try to compile, and notice it's taking a long time. I can see my CPU is running, and it's going. It usually takes a minute or two. There we go. So I get my little caret back, and it's ready. So having compiled the model, I can then use the model to combine the sort of priors that we had expressed in the model with the data to get out a sort of a representation of what we should believe now. So I haven't talked to you about it much, but the sort of black box stuff involved with Stan actually involves doing something over and over and over again. And iterations is the term for like how many times it's going to do that thing over and over again. It's best to use something like 1E3 or 1E4. These are really simple models, so large numbers of iterations like 1,000 or 10,000 will compute super quickly, so we might as well put it up really high. I'll show you why. For more complicated models, more iterations will take much more time. So for example, I've got a publication now that it took like 8 hours to do the inference. So a general sort of advice is to start with 200 and then work up to higher values as necessary. I'm going to start with 1E4 and show you what it looks like to have something that definitely has run for long enough, and then I'll step back and show you what it looks like when maybe it hasn't been run for long enough. So putting it for 10,000 iterations, I'm going to use the create this object called out. It's going to, in it, I'm going to put the result of running this big function here. So it's the sampling function inside the rstan package. The first argument object, we're just going to give it our model that we compiled here. The second argument data, well, we're going to give it the list that we packaged together. So put it as data equals data. I could have actually called this something like data for stan, in which case I'd have data equals data for stan. Chains is another thing that I won't talk about right away, but I'll remind me to come back to that. And then just this little bit says use the value we specified here as the number of iterations to use. You actually don't need these two because this is the default. But this last one means that if you were to run this on the same computer again down the road, you get the same results. There's something sort of quasi-random happening in this function that if you want to get the same result given the same model and data every time, you need to remember to set the seed. And so that's a good idea for replicability. It doesn't actually matter what number you put there as long as it's the same number every single time. So I just use the first number that comes to mind, which is 1. So running this, I haven't told you about what this is doing behind the scenes other than it's integrating data with our prior to establish what the posterior should be. So it gives some updates. It's sampled so quickly. It was done in like almost just a tenth of a second, less than a tenth of a second. For longer models, you'll actually see this gradually scroll by as it goes. But let's just see what this thing is that we obtained, this thing called out. Oh, I'm going to scroll over just a little bit and reprint it. There we go. So the output here, inference for stan model, and it gives the name of the file that we had originally had it named as. It says there's one chain, each with iter equals 10,000, warm up equals 500. Basically, whenever you give it a number of iterations, half of those iterations go towards something called warm up, where it sort of just tries to learn about the sample space that it's sampling for a little bit. So if half the samples are being put towards warm-up, it means the other half are being put towards actually sampling the posterior distribution. So we have one chain with 500 warm-up and 500 post-warm-up draws. So what's actually happening is that it's not able to literally do simple math to figure out what the posterior distribution is. It actually is doing something that allows it to obtain samples from the posterior distribution. So that's why we're talking about like samples and draws. Draws are another word for sample. So This next section tells about what sort of gives you sort of a numeric description of the samples or of the posterior distribution. So it's saying our posterior distribution has a mean of 101.27. Here's the standard error of the mean. That's actually not super useful. More useful is how sort of variable our posterior is. So we started out with a prior mean of 100 and a variability of 20. Now we've got a posterior with a mean of 101, so it's shifted away from sort of where we had it before, but it's gotten way narrower. That means that it's become informed by data. We're going to be more more confident that the true value lies somewhere close to this. In fact, you can actually ask, where is the sort of majority of the credibility in the where the value is. And so if you look at the 2.5 percentile to the 97.5 percentile, that contains 95% of the sort of samples from the posterior. Another way of saying that is that sort of encompasses 95% of the mass of your probability or your credibility distribution. So we're pretty confident that it's going to that the true value is likely between 96 and 106. These last two columns here indicate are measures of whether it thinks you've tried to sample for long enough. So if R hat is 1, generally that means that it's good, like you're good to go. You've sampled for long enough. Similarly, I usually like to ensure that NF, that's effective sample size. I usually like to make sure that's about 1,000 at least. So this is a numeric representation of the our posterior distribution. So let's take a look at the just a visual of that distribution. So this is going to use the ggmcmc package to visualize things. So there's a function called GGS. Actually, I wonder. There are some, since I did this a while ago, there's been some added things. Stan plot. Here. So if I look at the help for this, there might be some examples or plots for Stanfit. Okay. Let's see. I think I can just say now plot out, and I need to tell it what thing I want to look at. There's another row here called LP. You don't need to worry about that row. That's just something that I don't even really know much about or why it would be interesting to look at. So I want to plot the out. In fact, I'll put this on separate lines here. I want to plot the object that we got out of the sampling function. I want to say mu is the pars that I want to plot, and plot fun is histogram. This is actually going to create a ggplot plot, I think. Yay! Or not. Actually, that doesn't look like ggplot. There totally was a plotting that I saw before. Stan hist. Maybe if I say stan hist out not. Oh, okay. No, it is ggplot. Oh yeah, because it's the same thing. It's just is different coloring than I'm used to. That they've just applied a specific theme to it. So this, in the same way that we had our distribution reflecting our prior, that was centered on 100 and had a variability of, we had it as 20. This is now our posterior distribution. It looks like it's centered a little bit off 100. Indeed, if we looked at what that mean was, it's 101.27. And it's very narrow now. It's sort of very centered around the sort of 95 to 106 is the credible interval. So you can get a sort of rough sort of view of what the distribution looks like that. I thought I had. Well, we'll get into some cooler plots when we get multiple parameters. But so if you were to have this data, have that sort of set of priors that we had, and now want to write this up for publication, you'd write up what you had as your priors and your model. So really that, really these two lines. You then say, usually for a publication, it probably would be sufficient to simply say what the mean of your posterior is and the 95% interval here. Now this is actually called the 95% credible interval. That's in contrast to what you may have heard of before as the 95% confidence interval. Computationally, if we were to use an absolutely uniform prior, and if it were a simple model like this, the 95% confidence interval would be the same as the 95% credible interval. We haven't used, and I mean that as in terms of mathematical values, we haven't used a uniform prior, so the values are going to be different. Usually the credible interval is actually going to be a little bit narrower because we've used prior information. But critically, the interval reflects the thing that most people interpret a confidence interval as meaning, which is sort of the range of likely values. If you sort of consider the center 95% of the mass of this sort of distribution as the more credible area, this 95% credible interval reflects the sort of general area for where you believe that the true mean should lie. That's what most people think that the 95% confidence interval is, but it's not. It has to do with imagining many different experiments in an imaginary world where a hypothesis has a certain value and the rate at which you will capture the true value. It's a confusing thing that people get wrong. So you just report sort of where the mean was, what the credible interval was, and there's your sort of stats for that sort of experiment. The standard error of the mean, that's like how so you don't need to know about that. That's the mean. The SE mean is the standard deviation divided by the square root of the number of samples. So square root of 5,000. Let's actually triple check that. So 2.74 divided by square root 5,000. Oops. About 0.4, and that's what is there. So yeah, that is like kind of how confident you should be in this. It's actually not really. Yeah, no, it's not useful. This much more useful is these values. Yeah, I mean, you can just do more samples to make this approach 0. So it doesn't make a lot of sense to attend to this at all once you've got enough sort of effective sample size. So what would happen if I actually didn't do sort of enough sampling iterations here. So let me drop this down to 20. So went super fast. And let's look at the results here. We get a different result. That's partly due to randomness, but you'll also see that it says we only have an effective sample size of 10 and our hat is not 1, so it's kind of indicating to us that something's, we haven't sort of tried hard enough. A general suggestion is to start at 200 and then work up double every time. If you run through and you find you didn't have the R hat in particular that you wanted, okay, so it's 0.99, not quite 1, so maybe I'll go to 400. Yeah, pretty much sort of to its own representation of the number. It's pretty much 1. I like to still also increase till the effective sample size is 1,000. So if I don't know, I'll put this up to 1,000. Let's see, do I get 1,000 effective sample size out? No, not quite. So I'll increase it again. Oh, that's because the 1,000 means post warm-up draws of 500. So what if I put this up to 2,000? Close. Put it up to 2,500. I mean, this model samples so quickly that, oh, interesting. My effective sample size has actually gone down. So the effective sample size has to do with really what's going on inside, and ideally from one sample to another, there's no correlation in what you're doing, how you're sampling from the distribution. But there can be just random correlations that happen, and that will reduce your effective sample size. If you have a really hard to sample model, that will also induce a correlation, but you just have to sample for long enough. All right, so I put it back up to 10,000, and we should get those results that we had before. Certainly more than 1,000, so that's fine.
So why would we start at 200 if we know that we want more than 1,000 anyways?
Yeah. So the original suggestion I received was that the Stan folks suggest is start at 200. I think it's because they're maybe not as into the doing the 95% credible interval as maybe I am. Because I just take the approach that if you just have a set of data and you want to estimate the 2.5 and the 97.5, that you need to have at least 1,000 data points to do that at least somewhat reliably, so that you actually are so you have the 25th element and the 975th element. That establishes what the that range is. So that's my quick and dirty rule. So yeah, you're right. If you wanted at least, so it makes sense to start at 2,000. Yeah.
And then this is exactly the same as the 10,000 one that you did before. Is that right?
Yes. Yeah. Yeah, because I did the same seed here. I get the same result. Now, another thing so somewhat implied by the fact that I'm setting the random seed, something random is going on inside this sampling. So it actually makes sense to not just do it through once, but maybe have it run through a couple times. So that's what this chains thing is about. It's going to, a chain is another term for just how many times you run it through. Each chain starts at like a different place. If you think of this process as trying to search the space of whatever parameters are uncertain. So we just have one parameter that's uncertain, so it has to do a search along a one-dimensional axis. each chain is going to start at a different point on that axis. And it has some sort of random way of searching that axis to eventually get to a point where it's creating these samples from the posterior distribution. Good idea to put, say, chains equals 4. It's going to have 4 different sort of independent searchers going along. If I run it just like this, each chain's going to go one after another.
Do you have to take out the seed because if you've got it running like multiple times,
It will automatically, good question, it will automatically know that if we have multiple chains, it will use this seed to then generate 4 new seeds, one for each of the chains. So this is still used to establish what the seeds are for the other ones, so it's still replicable. If I rerun this, we'll get the exact same results, but each chain has its own random sort of thing starting point. So again, this model runs so quickly, it doesn't actually matter that each chain has been run one after another. They've been run in serial, but you actually can, I guess I didn't need that. I'll just comment that out and put it back to 1. If you're running multiple chains, you can run them in parallel. It works best, or this is most worthwhile when you have a scenario like I had, where it took 8 hours to get up to the effective sample size I needed, so I decided to run 4 of those at the same time. So that's the cores argument here. Most of your computers have probably at least 2 or 4 logical cores that it can be doing things at the same time. So that will do all 4 at the same time, and that they all sort of end at the same time. That was actually a scenario where it's actually slower to start up them on separate cores than do them in serial, just because it's such a fast thing. But you'll notice you'll get 4 times the number of samples in your posterior. So yeah. So let's go to the next example. For anybody following along in the files that I showed you where to download the other day, this was the example 01. And we will go up and go to number 2. So I'm going to close this. I guess I'll save. I'll close and open up this. I'm going to set the workspace, set the working directory here. I'm also going to run the command to clear the workspace. So now our environment is clear. RStan is still loaded, but it doesn't hurt to rerun this. We're going to generate some fake data again. It's going to be one group, and let's actually switch to the camera. There we go. I'm still recording, right? Yeah, good. All right, so it's going to be another scenario where we've got some IQs, and we're going to have a generative model that's a normal distribution. This time we're going to be uncertain about where the mean is, but we're also going to be uncertain about what the variability is. Now this would be much more typical in the real world. So the original example where we had uncertainty about where the mean is, but we decided to be certain about what the variability of the data generating population is. That's akin to the z-test or the z distribution when you're doing frequentist statistics. Here, where we are uncertain about where the mean is and uncertain about the variability, now you're starting to get into something akin to what the t-test would be, for example. Still, we're only talking about one group we're going to have a population, we'll sample from the population, and want to do inference on what the, given the sample data and what our prior beliefs are, what is the true value in the population for mu, and what is the true value in the population for sigma.
Does it matter the size of your sample?
It certainly does. So in the sense that the larger your sample is, the better your estimate of what the population values for those parameters are going to be. Yep. So just like in frequentist world, more data is better. You'll be more confident in your conclusions, in your beliefs.
But you could use with small sample.
Yep. So in the same way that we need to generate a, I'll just abbreviate it CR, credibility, a prior on the credibility for where, for the various different values that mu can take that will maybe sort of establish as a distribution centered on 100. So 100 is our peak sort of thing that we believe about. And maybe we have a variability here of 100, v equals, I don't know, 20, for example. In the same way that we have to establish what our prior belief, having not seen any data yet, about what we would believe about the population's true value for mu, we need to have a distribution now. If we're going to be uncertain about what sigma is, we need to have express a distribution for what sigma is. Now, we chose a normal distribution for mu. The normal distribution goes from negative infinity to positive infinity. With IQ scores, that probably doesn't make a ton of sense, but we're going to go with it for this case. It's a little bit more critical that when we talk about the credibility for the sigma value, that we can't go below 0 because a normal distribution with sigma equal to 0 isn't defined. Like, it's not a thing. So sigma has to be greater than 0. So you can even sort of express that. So sigma is definitely greater than 0. And we can express that using a distribution that has a bound, a hard bound at 0. So normal distribution goes negative infinity to positive infinity. A distribution that has a hard bound at 0 is a log normal distribution. That has sort of a shape, depending on what we choose for how it's shaped. A log normal generally sort of has a shape that kind of goes like that. So it has a peak, and it tapers off to each side. It tapers off more strongly on the side that's closer to 0, and it tapers off more gradually on the positive side. So, or on the side that's more strongly positive. So that's called a positive skew to this distribution. So we can choose like what values we might believe about the original population. So we know that in the same way that we chose the peak for this mean of 100, not 1,000, based on previous research on IQ establishing that the mean of a population tends to be about 100. The standard deviation of a population tends to be about 15. So we might sort of set up this log normal so that the peak here is 15. And to be sort of, we can establish what the breadth of this is. There's another parameter in the log normal that establishes what the variability here is. And we might make that sort of sufficiently broad so that we believe, I don't know, say this value is 30, and I guess that would skew this axis. So I haven't call this value 20. There we go. And so this value would be 10. So that sort of is a variability of about 5 for the value.
Wouldn't it be different because the right-hand side is more?
Yeah, so you'd start to believe you have sort of a sharper decline in belief on one side than the other. That actually tends to make things a little bit sort of more robust in that when you have sort of outliers in the data or whatever, those are going to drive the variance up. So you might believe variability to be a little bit higher than, there are scenarios under which it makes sense to have that positive skew and continue to believe larger values at greater rates than smaller values. So there's other distributions we could choose. Log normal is just one common one for talking about variability parameters where you have to have the hard 0 bound at the bottom. Okay, so this is then our model for the data. We've got a generative model where we're saying the IQs are going to be a normally distributed population with some mean that we want to do inference on and some variability that we also want to do inference on. We know variability has to be greater than 0. So we express a model for our belief in where the mean, or a credibility for where the mean, or various different values for the mean. So peaked at 100, but tapering off to either side. For normal distribution, but with a sort of variability parameter of 20. And ditto, we have a distribution reflecting our beliefs for where sigma might be, peaked at about 15, but a little bit of variability on the other side. So that, I believe, is expressed here. Okay. Files, stand, and pop out. Where to go? There it is. Okay. So same bit at the top here, little title, data is coming in exactly as before. Now there's two things in our generative model that we're uncertain about. Mu looks the same as before. We're saying it could take on any value. And sigma. But here we're expressing that sigma can only take values that are greater than 0. So we're expressing the lower bound on sigma. Notice it's these sort of, we use the greater than and, or sorry, less than and greater than symbols there, but they're just used as brackets basically. So we're saying sigma is bounded, to take on any value that's greater than 0. It's bound, it has a lower bound at 0. Down here in the model section, we're saying the data observations Y are modeled as a normal distribution with some mean and some variability. We've got our sampling, or our prior expression of the prior for mu here. So it's distributed as normal, centered on 100 with about 20 for the variability. Now, sigma, as I told you, it's log normal, but I said it would be centered on 15 and have like about 5 variability on either side, but here it's 2 and 2. That's because the units of this log normal distribution are on the log scale. So if you want to get out, so if we say x of 2, well, actually I said 7, didn't I? And so if I do x above 3, that gets us to 2.5, 2.6. Close enough. Okay, so I'll go back and I'll actually modify my priors. Instead of having it'll be a log normal with centered on 2.7, which turns out to be 15 when you exponentiate it, and a variability I said of 5, and that 2 is about 7, so I'm just going to leave that. So we've expressed our generative model, what we're uncertain about, our priors for each thing we're uncertain about, and the form of the data that's coming in. So I'll save, go back to our data. So this is going to generate some fake data. This one, I happen to be sampling from a normal distribution with a mean of 110 and a variability of 10. Again, we're going to generate this data, then immediately forget that we knew these numbers 1, 10, and 10. So we'll, as data analysts, we'll see just these values. And, oh, interesting, that worked. We can even just like eyeball what the mean of y is. So 108. And what's the standard deviation of y? Again, this is the mean of the sample and the standard deviation of the sample. We are going to be doing inference on the mean of the population and the variability of the population. So we package the data together to Stan, together to give to Stan. This still has the extra code that we didn't need that I had you guys delete. It actually just checks to see if it's already compiled. That already exists now in, oh, yes. It checks to see if it's already compiled. If it hasn't been already compiled, it compiles it and saves it. You don't really need that because these compile fairly quickly. So this is the exact same thing as we had before. This time we're referring, again, we've changed where our working directory is, so R can see this, and we give it the name of the file we want to compile. And while that's compiling, I'm going to change a couple things. I'm going to put this to 2E4 so that half comes out, or no, I'll just leave it as 1E4 because I'm going to say multiple chains. Actually, it is probably fast enough that serial is still going to be faster. So again, this would be like the one sample t-test where
Just on the screen, even not knowing any value, you put values there. Why? I'm sorry.
so you're talking about here? Well, it's just like the first, I was just expressing what the prior is for the variability parameter. So it turns out, there we go. So I wanted a log normal distribution that has this shape, peaked at 15. It turns out that just the way that Stan has implemented this distribution, the number that goes here, if you want to get what the value on the real number line is, you have to exponentiate it. So 2.7, I guess, e to the power of 2.7 ends up being 15-ish. E to the power of 2 ends up being 7-ish. So close to what I wanted there. All right, so that should be...
Excuse me, I have a question.
Yeah.
Can you go back to the
Yep.
previous slide? Log 0 is undefined because there is nothing raised to power 0.
Yeah.
Gives you 15 or 20.
Yeah.
So how did we generate 10, 15, and 20 exactly?
So when I say sigma, the lower value is 0. It automatically knows that to not try values of 0 for sigma. So it will never encounter that scenario of it not being defined. So maybe can you ask your question again, and maybe I missed.
Like log 0.
Yeah.
It's undefined.
Yeah.
Yeah. So I was wondering where we generated 10, 15, and 20.
If.
Why did we have 10? Like go back to the.
Oh, okay.
Yeah. Yeah.
This.
10, 15, and 20. Yeah.
Yeah. So you can convert this to log. So log 10 is defined, log 15 is defined.
Right.
So the log normal is actually just you take the raw scale and you take a log of it and put a normal on the log scale.
Where are the numbers coming from?
Oh, these are just potential values for sigma that are then going to be used. I just tried to scroll with my fingers, the paper. that are then going to be used to define how variable the distribution is that's generating the data. So before we had, in your previous example, we said sigma is 15. We are certain it's 15. Now we are uncertain. We think it's probably around 15, but maybe this population that we're observing is different from all the populations that have been observed in the past, and they've got a different variability from that. So that's where we say, okay, we have most belief in 15, but we still believe 20 a little bit, and we still would believe 10 a little bit.
Oh, okay.
Yeah.
But basically, they are arbitrary numbers.
They, sorry?
They are arbitrary numbers.
Yeah.
I'm not just using for.
Yes, yeah.
Can I ask my second question?
Yes, yeah.
What determines the variability? How did you come to that assumption? Like, what determines that?
This one right here.
Right.
So I happen to know, in the same way that I happen to know as a psychologist that IQs tend to be have a mean of 100. That's how the test was set up. It was also set up to have a variability of about 15. So that is just a property that they've tried to build into the test. So that's why I say I believe 15 the most, but one population might differ a little bit from 15. So
So it depends on the domain.
yeah,
How you work in there, you go for literature to see.
yeah, exactly. All right, so the model is compiled, so we can now run it, i.e. we can combine the model and our data to get a picture of the posterior. So I will run, and it runs really quickly. It'll say 20,000 post-warm-up draws. So we had 4 chains of 10,000 iterations each, but the iterations are split up into 500 warm-up, 500 actual draws. So we have 20,000 total. If I look at our hat, it's all ones, that's great. And F, they're all above 1,000, that's great. So I can trust what's in here. So notice now I've got the same row for mu here. In this example, I actually generated data from a population whose true value for the mean was 110. Our posterior is peaked at 108, so very close to that one. It's shifted from our prior, which we had in this, of we had our prior still centered on 100. So the posterior has shifted towards the mean of the data, and indeed the true value that we pretended to forget for a little bit. It's gotten far narrower. Again, that prior was had a variability of 20, but here the variability is like 1.6. So we're very confident that the true value is somewhere around 108. We can actually express what the 95, like the majority of credibility, where the majority of credibility is. It's somewhere between 105 and 112, which nicely actually captures the true value of 110 that we pretended to forget. Ditto, we've got a new line now called sigma. And this is what we should believe now about that variability parameter that we're doing inference on now. So this is the distribution that's now peaked at 9.5. It goes from 7.37 up to 12.37. So the true value that we used to generate the data was 10. So this credible interval nicely encompasses that true value. So if we were, again, not to know this true value of 10, we would conclude that from this, we would believe that the value is likely somewhere in here. And now when we refer back to the known value of 10, we know that that would have been an accurate conclusion. We can actually visualize both of those. Let's see. Where's the code from the last one? Well, this, let's see. If you just tell it to do the histogram without telling it what parameter to do, it'll actually do both. Let's see, how much time have we got? 12:51. Probably going to end it there. Just this is an example where we now are getting into more realistic scenario. Again, just one group. Next class, we'll start talking about two groups, and that's going to get us much deeper into real world type scenarios. All right, any questions? Great.